Hi everyone and welcome to this CoolLIFE tutorial. Today I have the pleasure to introduce our expert Adit Malla, who will demonstrate how the CoolLIFE tool and its calculation modules can be applied, guiding us through 7 use cases that meet various needs of different target groups. Over to you, Adit.
Based on the user needs identified over the course of the project, we have now formulated 7 use cases based on which CoolLIFE tool can be used to answer different questions or as per the needs of different target users. The first use case talks about strategic planning for energy efficiency and renewable energy integration, which is oriented for civil society, for policymakers, and also for technicians and energy planners. For this use case, we try to answer the research question on how can space cooling be integrated into the broader energy efficiency sector to improve strategic decision making at regional scale, also ensuring energy efficiency in residential buildings and having a better integration of renewable energy sources. This is a more of a holistic approach which the CoolLIFE platform can provide to answer the research question. We make the use of all calculation modules available in the platform in a structured way allows us to answer this research question. So firstly, we start with the space cooling demand layers, which allows the user to establish baseline cooling demand and the impact of efficiency, as well as to set up a default layer, a scenario projection based on which further assessment can be made. Then we use a space cooling demand calculation module to adjust the demand layers and make a more accurate prediction of the baseline. Following this, we use the technology and measures calculation module to assess energy use of decentralized cooling units and also consider efficiency improvements in these units and how it would impact electricity consumption. Then we look into the district cooling calculation module, which identifies high intensity cooling demand areas and evaluates feasibility of district cooling grids. Then we compare cooling intervention costs at different scales at local and at national and local levels, and then allows also identifying cost-effective measures that could best fit to meet the demand sustainably. And then we look into the demand side management calculation module, which allows us to align cooling demand with renewable energy availability and reduce peak loads through demand responses and strategies, and also look into the possibility of introducing PV modules into supplying the cooling demand, supporting in the integration of renewable energy. Then we come to the comfort, lifestyle, and user behavior, which analyzes cooling behavior and adaptive interventions, and also promotes behavioral interventions for demand reduction. Then the legal and regulatory framework calculation module allows the user to align with EU and national level policies and ensure compliance with regulatory frameworks and ensure that the strategic decisions and plans are aligned with these regulations. And finally, the financial mapping instruments allows the user to identify funding sources for cooling solutions and explore public-private partnership for financial support on actual implementation of the plans. So in general, the structured use of the calculation module supports informed policy making and evaluate demand, technology, and cost management, and also ensures alignment with energy efficiency and renewable goals both at the EU level and at national level. The use case 2 talks more about energy poverty and ensuring summer comfort, and also the target users for this use case is quite wide, including technical people from technical background, but also NGOs and civil society, which could contribute towards reducing energy poverty. So for this calculation module, we try to answer the research question, how can space cooling interventions be designed and implemented to reduce energy poverty while ensuring equitable access to summer comfort for all households, particularly in vulnerable communities. And for this, we see 4 calculation modules using an order that could best fit to answer these research questions. So first, making use of the economic feasibility calculation module, we are able to assess affordability of cooling solutions for low-income households and compare costs for passive and active technologies to identify cost-effectiveness options, and then support policy design for financial aid and equitable cooling access. In second step, we then use the comfort lifestyle and user behavior calculation module to analyze household cooling behaviors and adaptive practices, and then design awareness programs for efficient cooling habits. And thirdly, with the legal and regulatory information mapping, we can map policies affecting cooling affordability and access and identify regulatory barriers and opportunities for equipment solutions. And finally, with the financial instruments, we can identify funding mechanisms at low interest rates, facilitate adoption of efficient cooling technologies for low-income groups, and also address financial barriers to ensure widespread cooling access. So with this, combining these calculation modules, we ensure targeted and cost-effective cooling solutions and support long-term access of sustainable cooling for vulnerable communities without increasing financial burdens. Use case 3 talks about more of a planning on strategic and local level as well as building level aimed for low carbon energy efficiency, efficient space cooling. And also here, there are a very wide range of target users, starting from public administration, policymakers to energy consultants, as well as citizens themselves and energy communities. Here also we make use of a number of calculation modules to answer 2 main research questions on how can space cooling interventions be scaled beyond individual buildings to a strategic low carbon planning approach that aligns with long-term energy and climate targets, and how can cooling interventions at building scale be optimized to reduce energy consumptions while ensuring economic feasibility and regulatory compliance. So here we start with the technology measures calculation module to optimize cooling technology adoption for large-scale planning and also to see the effects of efficiency improvement on building level cooling demand. On a local level, the district cooling module allows identification of high demand areas for district cooling, whereas on a building level, a building owner can assess connection and cost effectiveness of district cooling. The economic feasibility calculation module then allows the comparison of cooling costs for large-scale planning and on a building level ensures financial viability of building level solutions. The demand-side management calculation module then aligns cooling demand with renewable energy and optimizes PV self-consumption and load shifting. And then we come to the user comfort, lifestyle, and user behavior, which integrates behavior aspects into cooling strategies and allows on a building level to promote adaptive cooling for energy savings. And then for the legal and regulatory calculation module, this allows the user to comply with national and EU regulations and also leverage policies for efficient cooling adoption. And finally, the financial mapping instruments calculation module allows on a local level to secure funding for large-scale cooling projects and support building level efficiency with financial aid. So this combination of these calculation modules allow the development of data-driven cooling strategies for regional and building spheres. It ensures economic regularity and technologies feasibility for interventions and supports sustainable energy efficient cooling at all levels. Then we come to use case 4, which talks about supporting data-driven space cooling interventions for technicians. Here, the target users are mostly coming from a technical background. So for this, we make use of most of the technically developed calculation modules to answer the research question on how can space cooling data be utilized to support engineers and energy consultants in designing effective cooling interventions based on building energy consumption and demand patterns. Here, we start with the technology and measures calculation module, which allows the estimation of cooling energy used based on climate and system efficiency, and then assess demand scenarios for technology adoption and efficiency gains. Following that, we make use of the district cooling calculation modules again to identify demand areas where district cooling could show feasibility, and then we evaluate grid potential to improve efficiency and cut costs. The economic feasibility calculation module would then provide the possibility of comparing the costs of passive and active cooling solutions and assess financial viability for cost-effective interventions. And finally, the demand-side management calculation module allows the user to align cooling demand with renewable energy generation and optimize PV self-consumption and demand response. So with the set of these calculation modules, the user can use a data-driven approach to design efficient cooling interventions, ensure cost-effectiveness, sustainable cooling through technology and demand-side strategies, as well as support transition to energy-efficient and renewable-based cooling solutions. The fifth use case is talking more about behavioral change and for energy savings in space cooling, and these are mostly designed for target users such as public administrations and civil society. Here we make use of 4 calculation modules to answer the research question: how can behavioral changes and adaptive cooling practices contribute to reducing energy consumptions in public and private buildings, and how can they be effectively integrated into space cooling strategies? So here we start with the demand side management calculation module, which aligns cooling demand with renewable energy and promotes pre-cooling and load reduction strategies. The comfort lifestyle and user behavior calculation module helps analyze cooling habits to optimize energy use and encourage natural ventilation, shading, and set point adjustments and other passive measures for reducing demand. The mapping legal and regulatory information calculation module ensures policies of energy efficient cooling are enforced on EU and national level, as well as use of building codes to support demand side measures are implemented. And finally, the mapping financial instruments provides incentives for efficient cooling and awareness programs and supports energy saving habits with grants and subsidies. So with a combination of these calculation modules, we can promote behavioral change and demand side flexibility to reduce cooling energy use, align policies and financial incentives to support energy efficient cooling practices, and ensure long-term sustainability in public and private buildings. Use case 6 talks about integrating space cooling into energy communities, and particularly designed for civil society, public administrations, and to be applicable for the use of citizens themselves. Here we again make use of 5 calculation module combination to answer the research question on how space cooling could be integrated into energy communities to enhance collective energy management and improve energy efficiency and ensure shared benefits for participants. So here we start with economic feasibility to compare costs of passive and active cooling for the within an energy community and ensure shared investments that could lead to financial and efficiency benefits. Then we come to the demand side calculation management calculation module, which talks about shifting loads to match renewable energy generation and use load balancing and peak demand reduction for improving efficiency. And then we make use of the comfort lifestyle and user behavior calculation module to analyze community cooling demand and behavioral patterns and promote shared cooling and adaptive practices to optimize use. Then we align shared cooling solutions with EU and national policies and identify regulatory barriers and opportunities for implementation with the legal and regulatory calculation modules. And then we look into sector funding through subsidies and grants and EU programs and support energy efficient cooling investments in communities with the financing calculation module. With these combination, we are able to integrate space cooling into energy communities for collective energy efficiency, assess economic, behavioral, and regulatory factors to ensure feasibility, and leverage financial support and demand side flexibility for shared benefits. And then we come to the last use case of providing inputs to national level comprehensive assessment report, which could be of interest for National Energy Agency, policymakers, national regulatory bodies, and consultants supporting policy implementation. For this, we try to answer the research question, how can national level assessment of space cooling as required by the Energy Efficiency Directive support the identification of cost-effective efficiency measures to promote the integration of district cooling and align with long-term decarbonization and energy security targets. For this, we specifically developed the economic feasibility calculation module to meet the needs of this use case. So, as per the requirements of the EED, which needs data collection, technical potential, scenario development, cost-benefit analysis, and optimal solutions, the economic feasibility calculation module is able to provide the user with a first-hand information on what different measures of active and passive cooling technologies could help develop scenarios and policies for more sustainable development and growth of space cooling demand on a national level.
And that brings us to the end of this tutorial. Don't forget to read the description for more information about the CoolLIFE project and the links to our website, the CoolLIFE Tool, the wiki, and the CoolLIFE Knowledge Hub. See you soon!